we can finally arrive to the power diode that usually named as PIN diode, PIN diode. We discussed up to now many important aspects, but they were only considered for a PN junction. That was not a diode. To have a diode, we need two contacts, two regions where to contact the anode and the cathode, and where we connect this metallization and the external terminals. In order to have a good ohmic contact to the anode and to the cathode, the requirement is that the doping below the contact must be high. We need a P plus region and an N plus region on the other hand, to have a good ohmic contact. Otherwise, we get a shock barrier. In conclusion, we need an N plus layer between the low doped N region that is needed to sustain the reverse voltage and the cathode. This region N plus shown here will be the contact, but will actually be the substrate of the chip, or a diffused region. However, this region here is not thin, is quite thick. Is the substrate, maybe 100, 200 microns. Is shown here very thin for teaching purposes, because we want to see the active region, but this region is thick. This is not the case on the other end, that is very thin. This is a diffused region on the top of the surface. This structure is named a PIN diode because there is a pre-region, the N region, and the N minus region that is also sometimes indicated like an intrinsic region. Very low doped region is an intrinsic one. Hence the name PIN diode, because you have at the beginning of the power device area, you have this intrinsic region with two contacts, P plus and N plus, PIN. Which is the effect of this N plus region at the bottom of the device? There are two main situations. As a function of the thickness of this N minus region and as a function of the doping here, we can have two cases. When we reach the breakdown condition, the electric field at breakdown reaches 0 in the low doped region. This is the solid blue line. The depleted region then is entirely inside the N minus region. We call this kind of devices non-punch-through case, non-punch-through device, or NPT devices. It is clear that this depends on the thickness of this region, but also on the doping. You can increase the doping to reduce the thickness of the depleted region. The other situation is when, at the breakdown shown with dashed lines, the electric field does not reach 0 before reaching the N plus region. What happens is that when the electric field arrives here and you keep increasing the reverse voltage, the derivative of the electric field in the N plus region is much larger, and you have this sharp decrease of the electric field. The electric field is bounded more or less in the N minus region, however. But in this case, the electric field near the N plus region is not 0. We call this case the punch-through case, because the device is punching through, the electric field is arriving at the end of the N minus region. In the previous slide, it is shown that for the same thickness of the depleted region, you can move from the NPT condition to the PT condition, simply decreasing the doping. For the non-punch-through case, we have this relation for the breakdown. All the values in that equation are physical constant. You can substitute the actual value, and for the critical electric field we can assume our value, that is 200 kilovolts per centimeter. In the end, you get that the breakdown voltage is proportional to 1.3 multiplied by 10 to 17 divided the doping. This is the non-punch-through condition. It is a line, decreasing line, in the plane where the x-axis is the doping in the log scale, and on the y-axis we have the breakdown voltage in log scale. The numbers are significant for an engineer. If we want a doping, a breakdown voltage that is around 1000 volts, you can see we need a doping that is in the order of 10 to 14, even less, not more. And if we substitute this doping in the relation that relates the doping to the thickness of the depleted region, we will see that we need a thickness of the N- layer that is around 125 microns. In the following, we will see that 125 microns with 10 to 14 doping is a quite significant resistance. If the thickness of the low doped region, of the intrinsic region, is smaller than the double good D that we have just calculated, or the doping is reduced, the electric field in the device is no more triangular but assumes a trapezoidal shape. We can neglect the high slope area here and the high slope area here. The limit case for the non-punch-through, the limit case for the non-punch-through case is for a doping MD star in which the depleted region at breakdown is equal to the depleted region at breakdown, and hence we have the electric field that arrives exactly at the beginning of the N+ region before reaching the breakdown. If the doping is further decreased, what we have is that this trapezoidal shape. If the doping is very small, we can assume that the derivative of the electric field is almost nil. The electric field here is flat, and we get that the breakdown voltage for this region with the constant electric field will be equal to the critical electric field multiplied by the thickness of the intrinsic region. This is the maximum value that we can get. That is exactly twice the breakdown voltage for the limit non-punch-through case. These are the two extreme conditions when you exploit properly the thickness, because the other condition in which the electric field arrives here, for example, simply means that you are wasting a portion of the intrinsic layer. You don't want to do this. Hence we have two limits for the breakdown voltage. One is 1/2 ECR multiplied double D, and the other is ECR multiplied double D. In between these two cases, the more general case of trapezoidal field profile, you can simply calculate the area of this region that will be given by this equation, that's simplified taking into account that the derivative is proportional to the doping and multiplied by Q divided by epsilon, you can obtain this equation for the breakdown voltage of the punch-through diode in the general condition that is not the very low doping, not the non-punch-through case. In the end, we will have two values that we need to set to obtain the breakdown voltage: the thickness and the doping. And there are two design options: punch-through and non-punch-through diode. Punch-through and non-punch-through device this will be valid also for MOSFET, IGBTs, and other devices. The total design plane is shown here in this famous plot that is probably directly taken from Baliga book. This plot will show as a function of the doping and as a function of the thickness of the intrinsic layer, which is the breakdown voltage. Actually, we will work in the reverse of the direction. We will set the breakdown voltage and calculate which is the doping and the thickness. This straight line here is the non-punch-through case. We have seen the non-punch-through case here. Here there is no dependence on the thickness of the intrinsic layer, because the intrinsic layer is thick enough to deploy the entire electric field. You have a triangular electric field that with the electric field that starts from the critical electric field and goes to zero. In this case, you just have the relation between doping and breakdown voltage. And you can see that for a 10 to 3rd, that is 1000 volts, you need 10 to 14 doping. If the doping is decreased or the thickness is decreased, you enter in this other region where you are in the punch-through case. For very low doping, here 10 to 13, you have more or less a square electric field. The electric field is flat in the intrinsic region. This means that the breakdown voltage only depends on the thickness of the depleted region. And for a depleted region of 10 microns, you get 20 volts more or less. 50 microns, more or less 900 something. 100 microns, about 2000. We have seen where we need 125 microns more or less for the non-punch-through case. It is reasonable that for the same thickness of 100 microns, you get about 2000 volts in the punch-through condition, more or less doubled. This intermediate region here, where the lines bend, is the trapezoidal shape. This graph will show you how to decide the thickness and doping of the drift region of the intrinsic layer of a diode, but this is also valid for many other devices. There are small exceptions, but this is a general rule. The physical structure of a PIN diode. What we have seen now are just schematics, schemes. Also the shape was placed horizontally. This is a more realistic sketch of the section of a power device, that is a power diode. We will have a chip, a silicon chip, that is N+, the substrate is N+. Here the substrate is shown is very thick, could be 5–10 times thicker than this region. These bracts here show exactly this. Then we have the top layer, the AP layer, or the intrinsic layer, that is very lightly doped. On this substrate, the manufacturer diffuses the P plus region with the typical lithographic technology. You have a mask, you diffuse or implant the dopants, and you get this P plus region. On top of this, there will be oxide, defining the masks, and you can also diffuse or implement the anode metallization. The structure is very, very simple. This is a cheap technology, much simpler than digital electronics where you need 20 masks, many layers of metallization, a lot of diffusing structure. Another important point here is that the dimensions are big, more or less, but for a diode, yes, they are big. Here you don't need the precision of 20 nanometers. Here microns are more than enough. And this structure is big. The area for a typical digital electronic device from ear to ear there is less than 1 micron. In a real application from ear to ear there can be a couple of millimeters. These devices are macroscopic devices because there are tens or hundreds of amperes that needs to flow through them. The silicon oxide is also useful for passivation purposes. You cannot, if you have this break here, this break is full of defects, and because the first idea that you can have is I remove the oxide and I diffuse the dopant on the entire surface, and this will work. This will be even better because I have more area. This is not a good idea because at the end of the silicon chip there is a crack, there is a cut with a lot of defects, and this will cause a lot of leakage and also problems with the breakdown. This oxide is used for passivation purposes. This is the structure, but we now see that this structure has some differences. The P region here is curved. There is a curvature here. And in reality, if I think of this structure in the 3 dimensions, I will see that this mask in the Z direction will cause some spherical borders, curved borders that also have an effect on the behavior of the device. In particular, we will see during the next lecture the effect of the curvature on the breakdown, because as you remember from the physics lectures, when you have a curved electric field, the electric field increases. The effect of the points in increasing the electric field. And this curved zone will increase the electric field just here. And we saw that even a single point where the electric field is equal to the critical electric field will break down the entire structure. And we will study during the next lecture how to model and prevent these effects.